Welcome to The Explainer. Today, we're unpacking something absolutely huge in the world of AI hardware scaling, data center architecture, and frankly, investment strategy. We are looking at the Cerebras CS4. In an era where AI models are just ballooning in size almost daily, the physical constraints of our hardware are suddenly dictating the economics of the entire tech industry. It's a real game changer. So let's dive right in and see exactly how the CS4 is acting as a massive disruptive force. Here's a quick look at our roadmap for today. First, the new bottleneck in AI inference. Second, how the CS4 breaks silicon limits. Third, we'll look at the backpack design and liquid cooling. Fourth, scaling economics and the capex cliff. And finally, the disaggregated data center strategy. Let's get to it. All right, Section 1, the new bottleneck in AI inference. The extreme demands of modern AI are exposing some really critical, fundamental flaws in our traditional hardware setups. If you look at the comparison here, the contrast is literally night and day. On the left side, we have the standard GPU reality. You've got stacked memory that's heavily constrained by high bandwidth memory, or HBM, which effectively chokes the output to around 100 to maybe 200 tokens per second per user. But look over on the right. The CS4 execution model visualizes this massive leap straight to 4,000 tokens per second. We are talking about a 20 to 40x leap in interactivity. The CS4 fundamentally shifts the whole focus away from just batch process throughput, leaning hard into real-time, low-latency interactivity for agentic and reasoning workloads. To really get why this bottleneck exists, let's break down the physics of decoding on this chart. Notice the horizontal axis tracking arithmetic intensity, while the vertical axis tracks performance. See that light blue shaded area on the left, the decode zone? In that specific zone, the workload is completely starved for bandwidth, not compute power. You can see that dark blue line, the GPU's HBM bandwidth ceiling, trapping performance completely flat at the bottom. But then follow that massive vertical orange arrow. That shows the silicon gap. The Cerebras CS4 operates at an SRAM bandwidth ceiling that is literally orders of magnitude above where standard GPUs are currently trapped. So, how on earth did they actually pull this off? Let's move to Section 2, CS4 breaking the silicon limits. Tracking the generational leap from the CS3 to the CS4 in this table, it's pretty wild. Performance metrics like dense compute and memory bandwidth have practically doubled. I mean, we jumped from 21.6 petabytes per second to an astounding 43.2 petabytes per second of memory bandwidth. But look at the critical metric down at the bottom, memory capacity. Both generations are strictly locked at 44 gigabytes. That's a hard physical constraint driven by the sheer limits of SRAM bit cells you can fit on a wafer. And as we'll see later, it completely dictates their cluster scaling strategy. Now, the crucial point is how they achieved this massive doubling of bandwidth without expanding that memory capacity at all. The central silicon itself, the 5nm WSC3 wafer, is completely unchanged from the previous generation. It's the exact same wafer. Instead, as those thick orange arrows pointing inward perfectly illustrate, Cerebras used a deliberate brute force strategy. They pushed dramatically more power directly into the wafer, essentially doubling the clock speeds. This brute force power delivery is exactly what yields that insane 43.2 petabytes per second bandwidth output you see on the right. By feeding double the power and integrating upgraded liquid cooling into the exact same 5nm silicon gear, they extract double the clock frequency. And that cascades into doubled bandwidth, doubled dense compute, and doubled I/O capacity. The big takeaway here? It's all about system engineering over a traditional silicon shrink. For customers, that translates to double the interactive token revenue for the exact same hardware spend. It's brilliant. Of course, pushing all that extra power requires a total rethink of the physical rack. That brings us to Section 3, backpack design and liquid cooling. Deploying the CS4 follows this radically simplified modular process. First up, you pre-wire the rack with front-facing power modules. Second, the entire WSC3 computing engine, which is housed in this self-contained backpack, is literally just socketed right into the rack on-site. Finally, you connect the facility-level direct-to-chip liquid cooling loops. This highly modular approach actually accelerates deployment times by a factor of 3. If we pull that backpack apart, you get this really fascinating 3-layer architecture. Layer 1, over on the left, is the front-facing power delivery system, engineered specifically to push twice as much power directly to the face of the wafer. Layer 2, highlighted in that vibrant orange, is the core WSC3 silicon itself, housing those 44 gigabytes of SRAM. And layer 3 on the right in blue contains the rear-mounted direct-to-chip liquid cooling apparatus and the I/O interface. It separates the power and the cooling absolutely perfectly. Zooming out to the wider chassis architecture, the orange backpack simply slots into the rear of the rack frame, while the power delivery modules slot into the front. By totally removing the internal heat exchangers and relying entirely on facility-level liquid cooling, this design achieves 50% fewer mechanical components. That simplification heavily lowers manufacturing and assembly costs, which nicely offsets those much more expensive thermal requirements. And here is what that actually looks like in reality. A fully deployed CS4 rack houses 3 distinct pluggable backpack modules, which you can see circled here in red. Instead of housing just 2 wafers like they did in the previous generation, this high-density layout comfortably fits 3 massive wafer engines cleanly into a single standard rack footprint, complete with those yellow coolant flow lines visible running up the sides. But all this incredible density brings us to a rather stark facility reality check. While legacy topologies rely on standard airflow and rack-level pumps, the CS4 topology eliminates those entirely. With 3 overclocked wafers, a single rack is now pulling a staggering 125 to 135 kilowatts of power. To put that into perspective, that is enough power to run roughly 100 average homes, all crammed into one single rack. The reality mandate here is crystal clear. Modern data centers absolutely must natively support direct-to-chip liquid cooling loops. Legacy airflow just literally cannot handle this kind of thermal density. So, what does this all mean for the actual business side of running frontier AI? Let's check out Section 4, Scaling Economics and the Capex Cliff. $40 million. Yeah, that is the staggering initial capital expenditure required to scale concurrent long-context requests on massive frontier models, along with nearly 2 megawatts of total power. So the obvious question is, why is it so outrageously expensive? Well, this feasibility phase diagram maps out exactly why. If you track the horizontal axis for average input sequence length and the vertical axis for model size, a really stark reality emerges. As long as your setup stays in the bottom left corner, smaller models, shorter context, you remain in the safe zone, which is easily handled by a pure WSE cluster. But as you track that curve out to the right, pushing toward 1 million tokens of context on a 1 trillion parameter model, you hit that thick black line. That is the capex cliff. At this precise threshold, the number of systems required just to house the context jumps exponentially from 32 to 64, all the way up to 128 systems. The reason you hit that cliff so hard all comes down to memory distribution. In this 1.6 trillion parameter case study, the orange bar shows static model weights consuming about 55% of the memory. But look at that blue bar. At 1 million context length and 256 concurrent requests, the KV cache, basically the memory the model needs just to remember the ongoing conversation, balloons to consume 45% of the total memory. Suddenly, that hard physical constraint of 44 gigabytes of SRAM we talked about earlier becomes a massive, massive financial liability. However, there is a silver lining when we look at the capex modeling. While moving from a minimal 23-system configuration to a high-load 40-system configuration is a severely high upfront cost, check out the scaled efficiency circle on the far right. Because the setup pushes so many concurrent requests, token throughput effectively doubles. That drops the overall unit cost per token by a massive 50%. So essentially, you have to spend big upfront to unlock that massive long-term token efficiency. To survive these brutal scaling laws, data center architecture absolutely has to adapt. That brings us to our final section, the disaggregated data center strategy. The strategic imperative here is clear. You just cannot deploy the CS4 in total isolation for frontier models. On the left side of this data center topography, you have compute-heavy GPUs, handling the intensive prefill phase. That state is then passed over high-speed standard RASI Ethernet, which gives you highly efficient, rapid communication right across the network, straight to the CS4 cluster on the right. The CS4s then act as bandwidth-bound sprinters, executing the ultra-fast decoding. This is heterogeneous disaggregation, perfectly pairing high memory capacity with ultra-high token interactivity. But, and this is a big but, this introduces a massive new risk, the disaggregation dilemma. If you look over a 5-year timeline, the blue line tracking agentic caching shows prefill workloads actually going down, while the orange line tracking reasoning models shows decode workloads going up. The workloads are highly dynamic. Yet, as the gray box below indicates, when you buy heterogeneous infrastructure, you are locking in a fixed hardware ratio of GPUs to CS4s on the exact date of your purchase order. a static hardware ratio is highly unlikely to remain perfectly optimal as these AI workloads continue to evolve. Looking at the target roadmap, it's clear the CS4 isn't just a faster chip for today. Plotting towards their 2027 target, Cerebras is aiming for an incredibly ambitious 20x throughput improvement over the baseline. Through its unique SRAM token economics and its field-upgradable networking capabilities, the CS4 is really positioning itself as the foundational catalyst for all next-generation, heterogeneous, disaggregated AI data centers. Which leaves us with a really critical question to ponder. In an era where heterogeneous architecture is no longer just optional, is your current data center infrastructure actually agile enough to avoid that brutal capex cliff? Or are you locking into static ratios today and basically building for obsolescence? Thank you so much for joining me on this explainer. I really hope this helped you decode the fascinating, complex reality of AI hardware scaling. Keep questioning and keep learning.